So let's take a look at this one and see what's happening. The easiest thing to track initially is probably the sodium hydride. We have lost the sodium ion from that, but the hydrogen that was bonded to is picked up another hydrogen. Must have come from the molecule here. We can see this has turned into what we kind of refer to as a hot spot. And so, remember at this point, to complete the carbon's octet, it's got two hydrogens attached. It looks like one of those hydrogens has combined with the hydrogen in sodium hydride. So, for that to happen, think about the sodium, this bonded to the hydrogen. When hydrogen is bonded to a metal, it's usually the more electronegative element. So that's the aggressor. So when that bond breaks, it takes the electrons with it. And so this bond breaking from the hydrogen, or rather the hydrogen taking the electrons, it uses those electrons to pick up a hydrogen. When that bond breaks, those electrons retreat back to the more electronegative carbon, hence this anion we see here. Because now this carbon only has one hydrogen attached. And we can check that through formal charge. Carbon, of course, is supposed to control 4 electrons, as we said earlier. And with that lone pair, 1, 2, and then 1 from each bond, 3, 4, 5. That negative charge on the carbon is because a consequence of the reaction has been giving up one of its protons. So from the Bronsted-Lowry theory point of view, giving away its proton, it's acted as an acid. From the Lewis definition, it's also accepted control of those electrons when the bond broke, which also makes it an acid. For the sodium hydride, the hydride part specifically, it's picking up a proton, which makes it a base according to the Bronsted-Lowry definition. But as it accepts the hydrogen, it's donating, giving up control of its electrons, which is the Lewis definition of a base. So this is actually one of the examples where either definition works for us. Yes?
So on the test, will we be known, which one it is or which one we have to know, which one we need to describe, I guess?
It'd be very similar to this. You'd be given a reaction scheme like this. She'd have to point out which is the acid, which is the base, and also point out if the Bronsted-Lowry or Lewis definition were appropriate.
Okay.
Sometimes it'll only be Lewis.
Okay.
Sometimes it'll be both.
But it'll tell us which one to name, So
You
will
probably
it
just,
say?
it's always about the initial materials, these two chemicals here.
Will it say what theory you want us to use?
No, well, probably say just define these as Lewis acid and bases or Bronsted-Lowry acid and bases.
So the first step was always defining which components have the higher electronegativity to see which ones are then going to be the ones that are stripping the hydrogens and giving it to the other ones.
Higher electronegativity normally tells you which way the bond breaks,
Yeah.
who's going to be taking and who's going to be losing the electrons. So sodium hydride is a very strong base. Oh, I worked with it during my PhD. You don't accidentally put sodium hydride in water and not wake up from that experience. Very aggressively looks for hydrogen from water. So think about if there's a charge, what does that mean for the carbons in their octet and how many chemical bonds are left compared to where we started? Electrically neutral here because it does control 1, 2, 3, 4 of the 8 electrons around it. Okay? Making sense. Let's take a look at the second one. All right. So, over the course of the reaction, we have now formed this new chemical bond between the two molecules. Nitrogen to boron bond has formed. That's the new part. And how did this happen? That would have taken a pair of electrons. Where did the electrons come from? Well, if you remember some of your earlier chemistry, you're probably aware that boron often breaks the octet rule. It often has an empty atomic orbital in its structures. And that certainly makes sense when you think of it from a formal point of view. Boron is the third element in the second row. And with those three, take that out in the bonds. With those three boron to hydrogen bonds, it owns 1, 2, 3 electrons, hence neutral as the structure suggests. So as a formal charge, you would have to show it. As we talked about in the lecture last week online, many textbooks get lazy when it comes to showing the presence of lone pairs. And the one thing we normally expect is that oxygen would have 2 lone pairs. Number of electrons it needs normally tells us the number of chemical bonds it has. So oxygen from its position, element 8. Count fluorine and neon, 2 more boxes, so 2 chemical bonds expected. But to complete the octet, everything else should be lone pairs. So we normally expect when oxygen is neutral, it's 2 bonds and 2 lone pairs, even though they're not initially shown, we just expected to realize that. And for nitrogen, from its position, we jump to oxygen, fluorine, neon, 3 more boxes. It needs 3 electrons normally to complete its shell. And that's through making 1, 2, 3 chemical bonds. So we normally expect a lone pair of electrons on a nitrogen atom. Even though we didn't show it, because chemists are sneaky, it jerks, that lone pair is normally in there. And so that's the source for making this new chemical bond. So what's going on here is the nitrogen using that lone pair to connect the 2 molecules. It's giving away control of its electrons. That's the definition for a Lewis base. The borane, BH3, is happily accepting those electrons, because of course it has an empty atomic orbital where those electrons can fit in. Accepting electrons. That's the Lewis definition of an acid. So it's all about electrons this time. No movement of protons, so it is just a Lewis acid and base. Bonsted and Lowry can't help us this time. So that's very typical, the kind of things we'll see on Thursday. Okay, yes?
What would the product be considered? Conjugate acid or base or both? Or
Doesn't fit into the bill because we don't have a pair.
Okay.
Yeah. Conjugate pairs is normally for proton donating and accepting chemicals. Okay, that puts chapter 2 to the sword. Oh, wish we had a bit more time for chapter 2, but maybe it's a blessing that we don't get too heavily into chapter 3, rather chapter 3 before the exam on Thursday. So let's do a little bit though.
Is the exam so fully covering equally chapter 1 and chapter 2?
Yes. So if you look at the old exams which are in that folder, on Desire to Learn, you'll see from one year to the next, you get some very similar kind of questions. If question 5 was acid-base chemistry in 2018, question 5 is probably an acid-base question in 2020. I mean, I'll change the questions, but I stick fairly close to what we've done in the past. I try and make up something new, but once you've seen one question, it's really difficult to ask anything really remarkably new. All right, let's take for just over 10 minutes, take a little look into alkane and cycloalkane chemistry. Hey, Captain.
Where's everybody?
There's a couple who can't make it on Tuesday, so they're just purely online, so recording.
What did you do to Sydney?
That's what I said.
Did you hear it?
She left me. I didn't do anything to her, she left me.
Okay. So alkanes are the simplest family of organic compounds. Boringly, just compounds that contain carbon and hydrogen. They always contain the full complement of carbon and hydrogen. So these are what we sometimes refer to as the saturated hydrocarbons, because they always have as much hydrogen as they can take. And that fits very neatly into a chemical formula. I see pens wiggling, so there might be some gaps here, so pause for a second. So Sid has even deserted the softball team.
What?
Sid deserted the softball team,
Yeah, she just left us. Because she thought she was too good for us.
I guess.
No, I'm just kidding. She didn't want to do it anymore.
She didn't want to do softball?
No, she's going to SIU. She's actually taking this class, like the lab for this class at SIU this
Okay.
semester.
Oh, do they let you do it different times, lecture and lab, don't they?
Yeah, the lecture lab, they have like lecture lab and workshop, and it's all like separated. It's really
Yeah,
great.
I always tell them, why don't we do that too? That people take it over an extended period, but I always get shot down. Let me just check that I started recording again. I think I did. I did. Cooey. So, whatever number of carbons there are in the molecule, you can double that figure and add 2, and you'll get the relevant amount of hydrogen that's in the formula. Tetravalent carbons, so you can double the hydrogens plus 2, and that will give you the chemical formula based on the number of carbons. We have names for them all. I'm only really interested in the first 14 for you to become familiar with. CH4, methane, C2H6, ethane, propane for C3H8, butane, C4H10, and pentane, like a pentagon with 5 carbons, double plus 2, 12 hydrogens, hexane, like a hexagon, 6 carbons, and then double plus 2, 14 hydrogens, heptane for a heptagon, C7H16, octane, like an octagon, C8H18, nonane, decane, undecane for 11, dodecane for 12, tridecane, and then tetradecane. That's as many as I'd expect you to be familiar with. To be honest, for the most part, we'll very rarely go beyond 8 normally. At the very least, if you quickly become familiar with the first 8 alkanes, that's usually good enough for most of the semester. Saturated hydrocarbons have twice as many hydrogens plus 2. Now, something that we'll get into more next week is that when we name hydrocarbons, we're looking for the longest continuous chain of carbons in the molecule. That sometimes gives us extra carbons that we haven't counted. So for example, 1, 2, 3, 4, 5, 6 carbons in a row, a longer sequence, that would be considered a derivative of hexane. And then those extra 2 carbons by themselves, 1, 2, this is what we refer to as a branch in the molecule. We can distinguish from the main chain to the branch by changing that name ending of A and E into a YL. So with 2 carbons in the branch, which would be based on ethane, we call it ethyl. It's that YL ending. So branches, if there's just 1 carbon in the branch, it's methyl, 2 carbons, ethyl. I sometimes revert back to my British days and say ethyl. Propyl for 3, butyl for 4, and pentyl, hexyl, heptyl, octyl for 5, 6, 7, 8. Subtract 1 from the hydrogen count to get the chemical formula of the branch. Because of course we need to get rid of that hydrogen so that we've got a pair of electrons that can be used to bond to the main part of the molecule. So as you see the names of these compounds, we can recognize the branch because it ends in YL. And it's also stuck onto the beginning of the name. We always, as we read the name of a hydrocarbon, the branch names come first.
Dr. Reed,
Yes.
should we note that that is, well, we noted with alkanes that it was CnH2n plus 2. Should we note that that is CnHn2n plus 1?
You can do. I mean, remember, it's only a part of the molecule, it's not the full thing.
Yeah.
I mention it really because you'll sometimes see a structure, a chemical structure listed for the molecule, and they will emphasize the branch as a separate part of the formula. Okay, so that's what it means. So just if you see it, think, well, hang on, how come it's not 12 or how come it's not 14? Because that's just a part, it's not the whole molecule, for the whole chemical formula. Again, if we look at some examples. So the core of the molecule with 8 carbons, so based on octane, also has 1, 2, 3 carbons in the branch based on propane. We take off the A and E and give it a YL ending. So we refer to this as a propyl branch. 5 carbons in the main chain, that makes that a pentane derivative, and with 1 carbon off the main chain, CH3, We call it a methyl branch. Notice that the branch doesn't include the main chain carbon. It can't be part of the main chain and part of the branch. So the branching doesn't include the core chain carbons. Nothing gets counted twice. Okay. Some of the background for hydrocarbons. It's a carbon tetravalent, normally sp3 hybridized. So those 4 chemical bonds around the carbon each time take up that tetrahedral stance, as we expect for sp3, with a bond angle roughly of 109.4 degrees. Looking at the main carbons in the chain, you see this kind of slight undulation back and forth, like the waves in the sea.
And a line structure for pentane or octane, if it's just the line structure, is it just kind of, we just put the ends with the 2 extra?
Just be like a weighted line, so if it was something like pentane, 1, 2, 3, 4, 5, it's back and forth. I put that on the page there. So just the carbon bonds, 1, 2, 3, 4, 5. This is for our YouTube viewers. Okay. Remember, working out the chemical formula, you've got a basic idea of the formula being Cn, Cn plus 2. So we don't have to count all the hydrogens. We can take for granted how many hydrogens are there if we know how many carbons there are. Just watch out for the presence of double or triple bonds and the presence of a ring. So exceptions for that rule. Every double bond or every ring of carbons that's in the molecule, subtract 2 hydrogens from your count. You make a ring, join the 2 end carbons together. That takes an orbital each time, so we lose a hydrogen from each carbon as they bond to themselves instead of bonding to hydrogens. So our first one, 1, 2, 3, 4, 5, 6, 7 carbons, following a CnH2n plus 2 logic. That'd be H16. Second one, start from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. Normally, we would expect double plus 2, which would make 26. However, we've got a ring here and a ring here, so we have to subtract 4 from that count. Every ring, subtract 2 from the hydrogen count you would expect for a saturated hydrocarbon. Last one, 1, 2, 3, 4, 5, 6, 7. 8, 9, 10. 10 carbons, no rings, no double bonds. C10, H22. Doesn't matter whether the rings are fused together or separate, every ring means 2 less hydrogens. And that, I suspect, well, we're actually out of time. Guess we have to stop. That's all right, give us a little start. I did put up as a Chem Talk video a little bit on naming alkanes, I think, this morning. I'm not sure how far it goes because there's 2 videos. That's probably beyond what we've done just now. Any questions before we head for the exits? Doing okay? Okay. We'll call it a day there, guys. Yay, we finally got to see each other on campus.